So earlier we mentioned a priori is one of the first algorithm created for mining association rules, and it does have some efficiency concerns. So over the time, there are not only new algorithms being proposed, but also methods that improves the efficiency of a priori algorithm have been also proposed. I thought it's interesting to look at those methods, even though, in this class, we're not going to programming the a priori algorithm, but knowing how to address some of the efficiency issues in computation would be beneficial. So I'm going to cover some elements of that. We probably won't get into much details, but give you some intuition. So the a priori algorithm for association rule mining has major computational challenges. We have noted that it needs multiple scans of transaction database, which are often huge. We know that the item sets can generate a huge number of candidates. The tedious workload of support counting for candidates. For every iteration, you have to count for every candidate across all the transactions there are. And we also noted a priori property are useful to proving candidates that are not viable. However, when you have a very dense database, the proving process are very slow. So the performance is not good for dense dataset. To improve a priori, and there are some general ideas, we can reduce transactions to be counted, right? If we can somehow remove the transactions from the database that won't actually change any of our decisions, then why do we need to scan and check on those transactions? We can reduce the number of transactions. We could also shrink the number of candidates, the candidate item sets. Maybe we can further reduce beyond a priori property could support. We can also reduce a number of database scans needed, or using other ways to facilitate counting of candidates. So I'm going to touch upon each of those in the following slides. So reduce transactions. The idea is to identify those transactions that's definitely not offering any information in future iterations. So if a transaction that does not contain any frequent k item set, then it cannot contain any frequent k plus 1 item set. Why do we have to scan them every time, every round? We should simply identify them at the round k and remove them from future consideration. So we don't have to scan them again and again for future iterations. The idea of reduce candidates. Remember our step 2, if we go back to this slide, so the initial candidate include all the unique items, and that gave us L1. Most often, all the unique items going to meet your minimum support count. So L1 is huge. And we know since every individual are frequent, and then its combination going to be even larger. So the C2 here, scanning DB for counts of the C2 itself is a major bottleneck. So what methods that we can actually use to address this issue? So when we're scanning the database to get the count for L1, we can already hash those transactions for all 2 item set. So for a student who's new to hash, let me explain what hash does. Hash is both a data structure and also a method. A hash function converts the input to a unique number. So if the input are the same, this number that's generated, we call it hash number or the hash value. The hash value generated are going to be exactly the same. When sometimes the input might actually be different, there's still a chance for the hash function to generate the same value. Okay, so if we give it a 2-item set, this hash function going to generate a hash value, and we can call it in this graph, this hash value is labeled as bucket address. Because we use mode 7 as the hash function, the hash value can only be from 0 to 6. So we have 6 buckets to save those inputs. So the idea is we want to find how many in each of the buckets, how many 2-item set were put into. And that's the count. So in this bucket, if I, 1 and 4, if we do order, so order of A is 1, right? So this is for order of B here is 4. So that would be 14. 14 mode 7 is 0. So this 2-item going to be put into this bucket. And 3, 5, 2 put into this bucket. And we can populate this hash structure and find that if we have a minimum support of 3, then none of those, the buckets with the bucket counts smaller than 3 cannot be frequent. So we don't actually need to consider those candidates anymore. So here we see that these 2 input, although the input are different, they are hashed into the same bucket. And their total count is less than 3, then their individual count can never be exceeds 3, right? Therefore, 3 and 5 cannot be, and 1 and 4 cannot be frequent. We don't actually need to consider them. Therefore, this method helps us to reduce the length of this candidate set. The next method is try to reduce database scanning. The number of scans, as we mentioned earlier, is too much. It's way too much. This idea is to let's partition the database. This partition will reduce the total number of database scans to only twice. No matter how long your frequent item set's going to be, this method only need to scan the database twice. So the idea is let's divide and conquer. The strategy that's used here is divide and conquer. First, we partition the entire database into K. Well, I should have used N here so that we're not confused with the K item thing. So we partitioned the database into N smaller parts. And for every parts, we adjust the partition's minimum support count by its transactions, by the number of transactions it has in this partition. Then we find all local frequent patterns. So no matter the length, all local frequent patterns that's identified in each of the partitions. The key observation that we have is if an item set that is frequent in the entire DB, then it must be frequent in at least one of the partitions, right? So we actually mine each partition to find the DB, to find the frequent item sets. So this partition may generate one set, this partition may generate two sets with their corresponding local frequent threshold. And then we can actually combine those together and do the second scan to find their frequent counts and drop some of the items that are not frequent globally. Okay, so that's the intuition. That can help reduce the number of database scans needed. Scanning smaller part is much more efficient than scanning the entire database. Another method that can reduce database scan is to use sampling. So we can, the original database may be very large, but we can select just a sample using a very low support threshold for the sample. We scan, we mine in the sample itself to find the frequent patterns. Okay, and then the next step is to verify if we have missed some. When you use a very low support threshold, the chance for you miss some frequent patterns is pretty minimal, but that does happen. So the method actually try to identify something called negative borders. Now we scan that once those within the sample, we can mine those candidate, the frequent item sets, and then we scan the database to verify those frequent item sets found in the sample are really frequent in the large database using the true support counts. And then also along the time when we're scanning database, we check to see if some negative borders of the frequent patterns mined from the sample are actually frequent. So if we have in the sample mined A, B, and AC, then we're going to check A, B, C, D. We add a new item there to see whether A, B, C, D might be frequent. If A, B, C, D are not frequent, then we're fine. We're not missing anything. But if A, B, C, D are frequent, then we're probably missing C, D, right? So if those negative borders are found to be frequent in the entire database, then those are the signals telling us that we have missed some frequent item sets. Then we will, now with this much smaller number of potential missings, we might need to scan DB multiple times to find the missing frequent patterns. But for a lot of applications using a very low support threshold, the chance is you only need to scan the database once to find the frequent patterns. So the last idea that we wanted to introduce is the idea of facilitate counting. And this method is called dynamic item set counting. The idea is to actually, while the database is being scanned, let's do multiple things at once. Let's don't do, so the original a priori method will scan the database to find the count for all one item sets, and then generate the two item sets and start a fresh scan and scan the database through, okay? The dynamic item set counting does things a little bit smarter. So when we do the one item set scanning, if we have decided both A and D are frequent, then we can immediately, while the database is still loaded in the memory, immediately start the scanning the counting for this AD two-item sets. We don't have to wait for this entire things being complete and the database is offloaded and then coming back and reload the entire database and do the entire scanning iteration by iteration. We actually can interlace them. Okay, so once we have sufficient information to start the third item count, we start right there. We actually don't need to wait for the two-item set to be completely scanned. So you can see that the next round of the scanning, we still make up what we have not scanned. That the part of the database that has been already offloaded, we make up those. The algorithm may be a little bit more complex, but we saved time. Okay, so those are the four methods, the four ideas that could be used to improve a priori algorithm for association rule mining. Next, we're going to introduce some more efficient methods that performs association rule mining.